Okay, now that you've gone through that simulation, what I'd like you to do now is go back to that blank sheet of paper. Again, I want to emphasize we edited our packets based on cycle 4 being a little bit different. So make sure that you staple that blank sheet of paper to your other packet just to stay organized. So let's go back to that. Now that you went through that simulation, I want to throw some real atoms on top of this and emphasize to you that this is now why molecular geometry is important, because pretty soon you're going to see how that molecular dipole you looked at affects so much about the molecule, specifically the way that it bonds to receptors. And that's very important when we start playing around with the COVID-19 ACE2 receptor. So, but let's take a quick peek right now. You saw that when you had a molecule like this, like let's say A and B, okay, and you saw when B had a greater electronegativity than A, we had a dipole area arrow going in that direction. Okay, that meant the electrons were closer over here. We also saw that we had a partial negative here and a partial positive there. Remember that it's not fully charged because B does not own those electrons. They're still shared. Okay, and we saw the situation reversed when A pulled harder than B. So first off, how do we know who pulls harder? So when you look on the periodic table, we're going to say that anybody to the right pulls harder. So people to the right have more protons in their nucleus. Protons are positive, electrons are negative. So they're going to pull harder on those. And I know you're gonna be frustrated sometimes with this because it's not a set way of thinking about it. For example, if A is up here and B is down there, or if A is down here, B is up here, or if they're side by side, B is still going to pull harder. So people more to the right on the periodic table have a higher electronegativity. That means they pull harder on the shared electrons. Okay, so let's look at some examples of ones like this. So this is the two molecule mode. So let's say that we had, come here, pen. We had a Lewis structure that was oxygen. O, O. Want minus half divided by 2. Okay. So in this case, there is no dipole area because no one pulls harder. Okay. Therefore, this molecule, what we call this is we call this molecule non-polar. So if there is no dipole arrow, or no molecular dipole, so in this case, you notice with these, there was no molecular dipole. So this molecule is non-polar, meaning there is no pull at all. So another example of something like this would be hydrogen, H, H. Okay. There is no difference in pull because the atoms are the same. Okay, they're not one is to the right of the other. So in both of these cases, the electrons in these bonds are chilling right in the middle. Boom, 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 boom. So there's no dipole area. Arrow. Why do I keep calling it an arrow and arrow? Whatever. So non-polar, meaning there are no pull. So if there is no arrow left over, it is non-polar. Okay, if there's no arrow, it's non-polar. And that's simple with the two atom model because there's no molecular dipole. There's either an arrow to the right or an arrow to the left. So when would there be a case when it would be polar in this? Well, if these atoms are different. So let's take a look now at something like HF. Okay, so F is more to the right of H on the periodic table. So F pulls harder on those electrons, meaning they're closer over here. That means F is partially negative and H is partially positive. Okay, and this molecule now is polar. There is a pull. Okay, another example of something like that would be carbon monoxide. Now you can get these bonds, by the way, doing 1 minus half divided by 2. Okay, now in this case, O is more to the right on the periodic table than C. It's got more protons in its nucleus, so it's going to pull harder. That means all the electrons are kind of congregated over here. So that's a partially negative, that's a partially positive, and this molecule is polar. Okay. So now let's take a look now, though, at what happens when we have that 3-atom model. Okay. So first off, let's look at something like CO2 that is linear. Okay. So, bye-bye. So we saw in this that C and O pulls harder on the electrons. Boom. But O also pulls harder on the electrons over here. Okay. So this is partially negative, this is partially positive, and this is partially negative. But what we ended up seeing, and we could take a closer look at this if we want to go back. Let's not go back. What we ended up seeing is there was no molecular dipole because this one canceled out this one. And there was no overall molecular dipole left. So this molecule would simply be written like this. And we call this molecule non-polar. Even though this bond here is polar, the molecule as a whole is non-polar. And that's what the molecular dipole is really looking at. Okay. But now let's compare that, and I'm going to do that right down here. Let's compare that to another molecule. Now, what if this was a bent molecule, like water? You know what? Let's actually not use water. Let's use a molecule like SO2. Okay, so SO2 is bent because of these lone pairs. Okay, now let's draw the arrows. Who pulls harder? Well, O is higher on the periodic table, so O is going to pull harder. O is going to pull harder here. Okay, now, what ended up happening when the molecule was bent? Well, whenever it was bent, we saw that we had a molecular dipole moving the direction. Think about it as a game of tug of war. If both people are pulling equally on each side, like in CO2, you're not going to have movement of the molecule at all. So there's no overall pull. But in SO2, because it's bent, this arrow goes in this way, this arrow goes in that way, so the overall arrow is actually in that direction. So the molecule itself, remember we can draw this on that side as well. This is a polar molecule. Negative, partially positive, partially negative. This molecule is polar. So again, if you have an arrow left over, the molecule is polar. If you do not have an arrow left over, the molecule is nonpolar. With the 3-atom model, that really applies to that molecular dipole there. And we can see in other situations, but basically, essentially, if the molecule is symmetrical, okay, on all sides, there's no bending or pyramidal to it, the molecule is going to be polar. If it's symmetrical, it's going to be nonpolar. We're going to have a cancellation of those. So the polarity and the nonpolarity of a molecule really ends up affecting its overall behavior. Okay, so perhaps you still have some questions about that, but we're just going to play around with this concept for a while. Okay, take care.